Okay, the rest of chapter 12 has to deal with solids, and section 6 in particular is where we're going to learn to classify solids according to a couple of different schema that have to do with their structure and their properties. So the first way that we can classify solids is according to the orderliness on the microscopic level. And so in other words, if you were to look at a solid material under, say, an atomic force microscope and look at the positioning of the atoms, they might be very orderly and regular. Not necessarily exactly this pattern, but some sort of a regular repeating pattern, and that would be a crystalline solid. This regularly repeating pattern has consequences that are apparent even on the macroscopic scale. So some crystalline solids are things like table salt, which has a structure that actually looks like this, and on the macroscopic scale, rock salt or large crystals of salt will have flat facets. Sometimes they'll even be cubic in their shape, and that occurs naturally, not because someone has gone to the trouble of making sure they cut all the little tiny salt grains into a perfect cube, but because forces of nature have caused them to organize themselves in that way. So that's a crystalline solid. And then some other solids will be a lot more chaotic. Sometimes there are gaps and sometimes they're close together. They just sort of exist where they exist. I hope I've done a good enough job of contrasting these two situations. This is an amorphous solid. And a good way to think of an amorphous solid is that imagine how a liquid looks on the microscopic level. All of the individual molecules are tumbling past one another. They're rotating, they're moving, they're flowing, and so there's a lot of sort of dynamic chaos on the microscopic level. Now, an amorphous solid looks like a snapshot in the movement of a fluid. So these are rigid, they're held in place, this is a solid, but the positions and orientations of the molecules are random and chaotic, just like if they were a flowing liquid. And so an amorphous solid is going to have the fact that it's amorphous is going to have consequences on its macroscopic properties. So one of the most interesting things about amorphous solids is that they don't have a distinct sharp melting point. So let's look at an example of an amorphous solid, chocolate. Glass is another good example, so we can think of both of those. Now, if I have some chocolate and I begin to warm it up, it will start maybe as a rigid bar of chocolate, but then it will become soft and bendy, and eventually it melts into a true proper liquid. Glass is the same way. You're in lab, in 1225 lab, normally we have a lab where you actually will melt, or you'll heat up some glass to the point where it becomes pliable and you'll be able to bend it and shape it and work with it. So glass will be a solid, and then as you warm it up, it will become soft and pliable, but it's not really a proper liquid, and then finally it will melt. Okay, now let's contrast that with a crystalline solid. Ice is a crystalline solid, water ice, and so if I have an ice cube and I hold it in my hand, it doesn't become like a soft and gooey, bendy ice cube. It's either a solid ice or it begins to melt on the outside and it's liquid water. There's no intermediate stage that's anything close to the way chocolate is if I hold chocolate in my hand. Right? So the reason why amorphous solids melt slowly and over a wide temperature range in this way is because some regions of the solid might be a little bit more open, have a little bit weaker of intermolecular interactions. This part will melt first. And other regions, maybe right here, for example, everything's all tightly packed and all of the attractive forces are sort of in their optimal orientation. And so that part will melt last because there's variation on the microscopic scale in how these molecules are structured relative to their neighbors. That's going to lead to a variable temperature at which they'll become mobile again. And so the entire substance will melt slowly over a wide temperature range with like this intermediate flexible soft state. Okay, so let me turn on our slideshow here. And just to reiterate, crystalline solids have a definite melting point. Something like ice or table salt are examples of crystalline solids. And then amorphous solids get softer as the temperature is raised, and eventually they will form a true proper liquid. And chocolate and glass are good examples of amorphous solids. Now, the next way to classify solids is based on the type of particle. So we've talked about different types of bonds, covalent bonds and ionic bonds. And so this is kind of building off of that. The idea is we're looking at how are the particles bound together. So something like a molecular solid contains individual discrete molecules. And I'll show you what we mean by that. Sorry. Let's look at carbon monoxide. Okay, so carbon monoxide looks like that. And when you cool it down cold enough, and it needs to get pretty cold indeed, but eventually it will form a crystalline solid. And you'll have carbon dioxide molecules that look like this. Oops. That should be a C. Okay, so it will form a crystalline solid that looks something like this. And it looks like we just have carbons and oxygens alternating every position, but if you look a little bit closer, you'll realize that this carbon and oxygen are covalently bound together with a triple bond. This carbon and oxygen are just next to each other in the crystal structure. There is no covalent bond. And so I can actually draw circles around each of the individual discrete molecular units. Within each circle, the atoms are covalently bonded together, and then in between the circles you have just these intermolecular interactions. In this case, it would be a dipole-dipole interaction that holds the molecules together in a crystal. So molecular compounds form one category of solid material. The next are ionic solids, ionic solids, let's look at sodium chloride, for example. Okay, so the sodium are the little atoms and the chloride are the big atoms. So sodium A plus and Cl minus. And they form a lattice like this. And just to really emphasize, I'll write plus and minus on a few of them. Okay, and this chloride right here is surrounded by some sodium ions, and it forms an ionic bond with each of them equally. I cannot single out any particular sodium and say, well, this is a formula unit. with a proper ionic bond, and everything else is just intermolecular forces. That's the wrong way to think about it. There are proper ionic bonds in every direction, and there's no meaningful way to divide this up into formula units that's better than any other way. There's sort of the strength of the attractive forces are equal in all directions. It's composed of ions, and so it's an ionic solid. Next are covalent network solids, and I won't try to draw one of these, but we'll see some good figures of covalent network solids in a minute. But these have covalent bonds, but they're really different than things like carbon dioxide and water that form ordinary molecular solids. Covalent network solids will have covalent bonds that extend from one neighbor to the next, to the next, to the next, to the next, across the entire bulk of the material. A good example of a covalent network solid is a diamond. Diamond is made of carbon, and the carbon atoms are all bonded together. And an interesting, if a little bit disingenuous way to think about a diamond is that it is one giant molecule. That's maybe true because there really are covalent bonds from one side of your diamond to the next. And then finally we have metallic solids, and we've not really dealt much with metallic bonds, and we're going to continue to not deal very much with them. But a metal with a non-metal forms a covalent bond. A metal with a non-metal forms an ionic bond. Two non-metals form a covalent bond. What sorts of bonds are formed between two metal atoms? Those are metallic bonds, and we will cover them really briefly here in this section. Okay, so if we look at each of these different classifications, we can get a bit of an idea for their properties. Molecular solids actually are the most diverse category here. You can have small ones like helium. The helium atom itself is the second smallest atom that we have, and it's going to have an extremely low melting point within just about 2 degrees of absolute zero. So that's the helium atom, or within less than 1 degree of absolute zero. All the way up to something like tetrasulfur tetranitride, and this is going to be a solid at room temperature. In fact, it doesn't even melt at all. It will sublime at 179 degrees Celsius, and so you'll have melting points that span a wide range. You'll have molecular compounds that are all phases of matter at room temperature. Some of them will be a solid even at elevated temperatures. Some of them will only solidify when you're a hair's breadth away from absolute zero. So those are the molecular solids. Ionic solids are a little bit more consistent in that they all have very high melting points. If you think about table salt, sodium chloride, you can put sodium chloride on the stove or in your food and it's not going to melt. You need a special furnace to get up to 801 degrees Celsius. And that's kind of the low end. Up here, aluminum oxide and magnesium oxide are in the thousands of degrees Celsius melting points. And that's because ionic bonds are so very strong. And then covalent network solids, things like diamond, graphite, or quartz, they also have extremely high melting points. They in the thousands of degrees Celsius, because those networks of covalent bonds are extremely strong. And then finally, metallic solids. Here we're looking only at pure metallic elements, but there is actually a surprising range. We think of metals as things that withstand heat. We use metals in our cookware and in our machinery and whatnot. But the reality is some metals have very modest melting points, like cesium here, 28.4 degrees. If you held some cesium in your hand, as long as you have good circulation, then you could melt that in your hand. Mercury, of course, is a liquid at room temperature. Its melting point is almost negative 40 degrees Celsius. So there are some interesting exceptions here, although there are other metals like iron and tungsten that meet our expectation of having melting points at thousands of degrees Celsius. Sorry, I should fix this table here, but if we look at molecular compounds, this is kind of just summarizing, right? This is the picture of what they look like, individual molecular units with some sort of intermolecular force that holds them together in the solid. Here we have water molecules held together by hydrogen bonds, and their boiling points can cover a wide range, but they don't get to the thousands of degrees Celsius, so they're very low to moderate. Ionic compounds are composed of ions, ionic bonds, and they have high melting points. Covalent network solids, here we have a picture of silicon oxide at the microscopic level, and they have very high melting points. And then a metallic bond. And here we're starting to see a picture of what a metallic bond might look like. You'll have the nuclei of the metallic atoms arranged in some sort of a crystalline network. And then the electrons, at least the outermost shell of electrons, are sort of shared and distributed between them in what's called an electron sea. Anyway, we'll actually get to that in just a little bit. Okay, here's your sodium chloride structure. It looks like what I drew on the board, only nicer. And here we have a couple of examples of covalent network solids. So on the left, there's graphite. It's composed of carbon that is bonded together in these sheets, and one sheet can extend, to macroscopic dimensions, and that is one form of carbon. And then on the right we have diamonds. Those are uncut diamonds, but they are diamonds nonetheless, and they have a three-dimensional covalent network that extends across the whole bulk of the stone. And then a Buckminster fullerene or a buckyball is a type of carbon where 60 carbon atoms are bonded together in this geodesic shape. And I would say that Buckminster fullerene is kind of the lower end of what we might consider a covalent network solid, and the upper end of what we might consider to be a true molecular solid, or a covalent solid. Is that a molecule, or is that a small sample of a covalent network solid? We're probably kind of at the boundaries. Okay, and lastly here we have the electron sea model. So for metals, the nuclei arrange themselves in some sort of an orderly pattern. It doesn't have to be a perfect square lattice. You see on the right, you have a lattice with a little bit of a zigzag, but the nuclei will arrange themselves in some crystalline pattern. And then the valence electrons, or the outermost level of electrons, are going to be shared not just between next neighbors, but across the entire sample of the metal. So covalent bonds will share electrons between two discrete bonding partners, but in a metallic bonding scenario, the electrons are shared not just with nearest neighbors, but shared across the entire bulk of the sample. This is called the electron sea model, because it's like the cation nuclei are floating in a sea of electrons. And because the electrons are no longer bound to any particular atom, they're shared between all of them, then they are free to flow around the substance. And that is why metals conduct heat and conduct electricity, because their electrons are mobile. They can literally move around easily, and so electricity can be conducted, and electrons will carry heat in the form of kinetic energy and quickly move heat from one side of a metal to the other. There is another way to look at metallic. Oh my goodness. Yeah, sorry. I just made the slideshow disappear, but it was on the whole time, I hope. Okay, so there is another way to describe metallic bonds, and that is through something called band theory. So you may recall in molecular orbital theory, if I have something like two oxygen atoms and they're going to come together and form a bond, well, I'll take their valence shell, 2s, 2p, 2s, 2p, and I'll construct new orbitals. I'll do a really sloppy job of this because that's a review. This is molecular orbital theory, where the orbitals or the energy levels from the two bonding partners will combine and mix and split. Well, if we take molecular orbital theory and we put it on steroids and say we're not just going to combine the energy levels of two bonding partners, but let's take 10 billion atoms involved in a metallic bonding scenario and combine all of their energy levels. Well, they're going to have instead of just these two splitting a little bit, you'll have, 5 million energy levels on this side and 5 million energy levels on that side, because you have so many bonding partners involved, and they're not just going to produce, 8 or 10 molecular orbitals. They're going to produce millions of energy levels, and those energy levels will be so close to one another that that they're no longer discrete. There's just like a continuum of energy levels here. Anyway, I don't mean to go into this in too much depth, but this is called band theory. And your energy levels become, they go from being discrete energy levels to being energy bands, which have continuous energy levels across a certain range. And there will sometimes be a gap here between the filled and the unfilled energy levels. So this would be what we call the valence band. And this would be what we call the conduction band. And the conductive properties of materials has to do with the size of that gap, whether there is a gap at all, and how far filled either of these bands are and things like that. So it can get really interesting, and it can become a very powerful theory for dealing with edge cases like semiconductors. Are they metals or are they non-metals? Do they conduct or do they not conduct? It can begin to depend on things like the temperature or the presence of tiny amounts of contaminant and things like that. And band theory is a really robust way to deal with that. So you don't need to really know anything about band theory, but other than that it exists and that it's a more complex and robust way to look at metallic bonds. Now, because the positively charged nuclei of the metals sit in this sea of electrons, they do not have very strong, usually, attractions with their neighbors. And so if you take a metal and you subject it to some sort of a force, then it's very likely that atoms will shuffle around a little bit. They're able to slide let's say I've got a situation something like this. Well, if I strike that sample of metal with a hammer, well, maybe these two molecules will move up one position. And I can deform and reshape the metal. Without it cracking or breaking, they just sort of move their position in the sea of electrons. And they are just as stable in their new positions as they were in the old positions. And that's why blacksmithing works. That's why metal wires can be bent, why metal can be pounded into thin sheets or stretched into wires. All of those great physical properties of metals that allow us to shape them and use them the way we want is because these metallic bonds make the nuclei able to shift and move in response to sufficiently strong forces. Okay, those properties are called ductility. So a metal is ductile, which means that it can be stretched and drawn into a wire, and the material is malleable, which means you can pound on it with a hammer and reshape it through a pounding force. And most metals have a really impressive amount of ductility and malleability. And that's it for 12.6.